পাসওয়ার্ড ঢুকে দাও তো টিউসডে ড্রয়িং ক্লাস হবে জানি ওই যে হ্যাঁ জানি যাও
Okay, sir. Then probably we can start because we have more than 50 students now.
Okay.
Okay. So welcome all the participants. So today is day 2, and we have the speaker with us. Now I request Professor Deka to carry over today's session. Over to Professor Deka.
Yeah, thank you, Ratul. Today we are on day 2 of this ElDeS webinar. Honorable Vice Chancellor, sir, and respected distinguished sir, and my dear colleagues. Today we have with us Professor Amit Sethi, I from IIT Bombay. A little like introduction of Professor Sethi I want to make here. Professor Sethi is a professor at the Department of Electrical Engineering, IIT Bombay, and an adjunct faculty in pathology at the University of Illinois at Chicago. He has obtained his PhD from University of Illinois at Urbana-Champaign. He works in the areas of image processing, computer vision, and machine learning. For the last few years, he has been working in deep learning and its application to digital pathology for analysis of cancer tissue images. He is a recipient of Facebook Ethics in AI Award, Patient-Centric Frameworks for AI-Enabled Medical Tests 2019, and Microsoft Young Faculty Award 2011. He is a review editor and guest associate editor for Frontiers in Oncology. He has published his works in reputed journals like IEEE Transitions on Medical Imaging, IEEE Transitions on Multimedia, IEEE Transitions on Pattern Analysis and Machine Intelligence, and Scientific Reports. So I request Professor Sethi to start his talk. I hand it over to Professor Sethi now.
All right. Thank you, Professor Deka and Professor Goswami. I thank you for this invitation to give a talk. I hope the participants here would find it interesting. So the topic that I will cover is towards precision oncology using machine learning on digital pathology. So what we mean by precision oncology is that when a person gets cancer, then earlier the treatment paradigm used to be that we would surgically remove the tumor if possible, if it is a solid tumor, and then we would give a cytotoxic chemotherapy, which means that we will give poisonous chemicals that will kill all fast-growing cells. And because cancers are fast-growing cells, hopefully those will be killed, but so will also be other types of fast-growing cells in the body, including healthy cells such as the ones in the hair follicles and so forth. That's why the hair falls off in cancer patients who undergo chemotherapy. But in the last 15-20 years, the treatment paradigm is changing, where there is emphasis on finding specific mutations that are driving the tumor, and each patient's set of mutations that drive the tumor can be different. And because of that, one size fits all is no longer the treatment paradigm. So we want to be able to find out what kind of which patient will respond to which therapy, so that we don't give unnecessary therapies or more cytotoxic, more therapies with more side effects to all patients, but only to patients who actually need it. And in that way we can reduce the side effects and hopefully save more lives. So the way this talk will flow is, I will give a little bit of introduction to use of artificial intelligence in medicine, and then I will talk about a few problems where my collaborators, my students and we worked on replicating the human expert, and then we will talk about how to go beyond the human expert also in using AI. And then we will also look at some of the challenges in the real data that we use in medical images, and then we'll look at uncertainty estimation in AI. Am I audible?
Yes, sir. Yes, sir.
Yes, yes.
Fine.
So a lot of advancement in AI has been in couple of areas, couple of types of data. One is imaging data and the other is text data, like the natural language data. So since I work a lot with images, I want to give a overview of where images are useful in managing the cancer treatments, the whole cycle of treatment of a patient. So here's an example of a breast cancer patient. So let's say when we want to do early detection in the patient, then we might do an annual mammogram, which is basically an X-ray. And these days, a lot of these X-rays are done in a digital form. So there's no film, it directly gets captured on the computer. And that image itself is tells you whether there is a mass inside the breast or not. So once there's a mass that is suspected, then we would do an actual diagnosis where we might follow it up with a MRI, or we might stick a needle and take a part of the tissue out to prepare a slide and see it under the microscope, which is the biopsy. And for basically seeing where the needle is going, we might do ultrasound also, and then see if there is metastasis. For that, we would do a chest X-ray. So all these are different imaging modalities that will help us basically take the tissue out, and then from that tissue we can prepare slides and we can see where the cancer might be, whether it and what kind of subtype of cancer it is. So once it is determined that a person has cancer, then sometimes if the cancer is too big, then the first line of treatment is that we try to shrink the cancer by giving something called neoadjuvant therapy. Neoadjuvant means before the surgery. We give chemotherapy before the surgery if the tumor is too big. So with the hope that it will shrink the tumor to a size where it can be extracted using surgery. So once we do any neoadjuvant therapy, then we would want to predict the response. So we would want to do another set of imaging, either MRI or chest X-ray and so forth, and see whether whether the tumor has shrunk or not. And we would also want to do assessment of the response to see whether it has actually shrunk the tumor or not. And then after that, if we do the surgery, then we will do another set of we would take the tissue out, and then we'll prepare more slides to see under the microscope, which is the surgical resection pathology. So this would be followed up by adjuvant therapy, which means that after the surgery has happened, there might be another round of chemotherapy where we would kill off any remaining cancer cells that might have escaped surgery. And after that, we would do another set of imaging to see whether the tumor has come back or whether it is completely gone or not. So you can see that the entire treatment cycle is guided by imaging, different types of imaging at different points. So now with these images, there are several challenges such as that we do not have enough experts to read these images. You can buy equipment and install them in remote places, but then there should be experts who are able to read these images, pathologists and radiologists. So if we don't have enough experts, then some of the gap can be filled, perhaps using software that can do the first level of analysis, and only the cases that are contentious can be sent to an expert. So that is one way of looking at it. Sometimes you can also use software to give a second opinion, and sometimes you can use the software to see things that humans cannot easily see. So I'll give you examples of these as we go along. So, is there any question?
No, you can remove the, you can hide the small screen.
Okay. All right. Okay. So when we have an image, there are multiple ways we can analyze it, going from most easy to most slightly more difficult and so forth. So let's say this is an image. This is basically a CT, computed tomography slice of the chest cavity. You can see the rib cage and so forth. So let's say this is an image that we want to analyze. The first level of image analysis would be to classify this image. So you would classify it into class 1 or class 2, let's say. And class 1 could be that there is no disease or no suspected lung nodule. And class 2 can be that there is suspected lung nodule. So each image has to be classified into one of these two. So that would be a classification model where it tells that there is a calcified nodule present or not present in the image. So let's say these are the calcified nodules. So these could be signs of lung cancer or fibrosis and so forth. The second level of analysis would be to detect the objects that we are using for classifying the image. So detection means we want to put a bounding box around the objects that we have located. The third level of analysis can be that we want to do semantic segmentation, which means we want to mark all the pixels that basically tell you where the object is. Okay, so here the green pixels here mark nodule 1 and nodule 2. And fourth level is instance segmentation, where we are actually predicting that this is nodule number 1 and this is nodule number 2. So we have marked them with different colors. Now here it is straightforward because these two nodules are not touching each other. But sometimes when you want to tell objects apart, they might be touching each other, in which case it's a slightly more difficult task to say that this pixel belongs to object 1 and not object 2. Okay, if they are touching each other. If they are not touching each other, then that separating the objects is straightforward. So these are different level of tasks that we can do. Then we can extend this to other types of tasks as well. For example, can we predict outcome of a treatment based on the image itself and so forth. So we'll come to that in a little bit. So as far as image analysis goes, now we have deep neural networks and methods for training deep neural networks that have achieved human level accuracy. So what does human level accuracy mean in this case? So this is the timeline from 2012 onward, when it whole started, and up to let's say 2017 and now 2022. And this is the accuracy of classifying images. And here we are looking at a very specific data set, which is the ImageNet data set, which has 1,000 different categories of objects. So for example, you have cat, dog, car, truck, aeroplane, etc., etc., and then different types of cats and different types of dogs, different types of other animals, etc. So there are 1,000 different categories of objects. And what we measure is how much is the error that is left in classifying unseen objects. So let's say out of these 1 million images, we use 800,000 images, 8 lakh images for training, and let's say we use 2 lakh images for testing. So there is a line here that says human level accuracy. So what does that mean? Why is it not 100%? Why is it not 0% error? That is because the images, when these images were collected, these images were collected by experts in their own fields. But when you ask an average human to classify them, sometimes they make mistakes. So for example, a husky dog looks very similar to a gray wolf. So they might make a mistakes on some of those images. That's why the human level accuracy is also not 100%. And now these neural networks have started to get more accurate compared to the human level accuracy. And the size of this circle tells you how many parameters, free parameters, there are in these neural networks. So earlier it was thought that if you want to increase accuracy, you have to increase the size of the neural network. But then with the newer architectural innovations in neural networks, how they are connected, the size shrunk again, and then it exploded again, and now it has shrunk again. So depending on the innovation, you can actually do more with fewer parameters in the model, fewer unknowns in the model. So now coming back to medical images, what can we do? How can we adapt this technology for medical images? So here we are looking at, let's say, taking a cohort of patients and dividing them into two groups. Let's say one group is case and the other group is control. So case means that these are the baseline patients, and control means that these are the baseline patients, and cases means these are the patients that we want to detect who have let's say slightly more severe form of a disease and so forth. So here what I'm showing is biopsy slides from a particular cancer, from breast cancer, and these are, let's say, slides of controls and these are slides of cases. Now what can I train neural networks to do? I can do basic level analysis, such as whether the slide is a malignant slide, that means it has a cancer, or whether it is benign. Benign means it could be normal, or it may have a disease but that disease is not cancer. Then I can make the problem more difficult by saying that within cancer slides, do another classification, whether it is high grade cancer or a low grade cancer. Then I can go one step further and say that, okay, let the neural network train to classify between different morphologies, different patterns that pathologists see in the cancer, whether it is ductal carcinoma or in situ carcinoma. Now up to here, it is basically replicating what a human already does. I can actually make the task of the neural network more difficult, where it starts to do things that humans cannot do. So for example, can the neural network predict whether there is EGFR mutation in this cancer or there is no mutation in this cancer? Now, how will I do that? How will you, as you might know, that these neural networks have to be trained using labeled examples. Most of the times they are trained using supervised learning. So where would the label come from? So the label can come from a more expensive test that we cannot do for all patients. So for example, we may be able to do DNA and RNA tests, for which we get some grant to do that for 1000 patients. From those 1000 patients, we find 400 patients have a particular mutation, 600 patients do not have a mutation. So we spend the money on the genomic test for these 1000 patients to amass the data. So that data is whether they have the mutation or they do not have the mutation. Now I go back to this inexpensive way of preparing slides, which has this pink and purple color, which is called H&E stained slides. Here, the hope is that because of the mutation, there will be subtle changes in the shapes of cells and how they bind with each other that cannot be easily observed by pathologists, and it cannot be taught by, even if an expert pathologist can spot it, they cannot teach it very easily to their residents. But once you can train a neural network to spot these differences, then that software can easily be replicated on other computers. Then we can make it even more value added problem by saying that let's let the neural network learn how to distinguish between someone who will respond to therapy versus someone who will not respond to therapy. And then we can also go ahead and say that, oh, let's predict short term, those who will not survive very long after the treatment versus those that will survive for many years after the treatment. So this way we can keep making the problem, the neural network, more and more valuable, or we can train more valuable neural networks and we can add more value to the test. But all this is right now is in experimental stages. Before it can be used in a clinic, of course, it will have to go through a lot of validation. Now, does that mean that this will replace the doctors? Absolutely not. Because a neural network is only good at very specific tasks on which it is trained. So let's say I train a neural network to do, or a couple of neural networks to do all these tasks. But in the training, I only showed it normal versus malignant, and at the use in the clinic, some other rare disease of the breast came and it was shown to the neural network. Then the neural network will be thoroughly confused. It will not be able to identify these boundary cases. It will not be able to identify cases on which it is not trained and so forth. Or let's say the image quality is very poor, then it may not be able to tell that I should not take a decision because these cases, the quality of the image is poor. Whereas a doctor will easily be able to adapt to new situations. So we would like to think of these AI-based tests as any test that you conduct in the medical realm. So for example, today when we say that, when the doctor says that go get complete blood count CBC test done, we don't even think about it. We just give our blood, it goes into a machine, it counts all the types of cells and so forth, and we get the result the next day. So similarly, in the future, they might use certain AI tools to conduct tests. They may order tests that go get this particular test, AI test done. And based on that, they will make the assessment about how to treat the patient. So that will be the direction in which this will go, as opposed to replacing the doctor. So what it will do is it will make the doctors more efficient. They will be able to analyze more images. They will be able to diagnose more patients in the same time that they have. So now, what are the challenges with training deep neural networks on medical images? So compared to some of the problems on which we see papers and research in computer vision research, there are differences in the images and the data sets that we have for medicine versus that we have for general computer vision. The first one is that the size of the images, medical images, is quite large. When you take a glass slide, a pathology slide, and you scan it at high resolution, then the size will be in gigapixel, not megapixel, but gigapixel. So it becomes such a large image, such as 1 lakh by 2 lakh pixels, that it is not easy to give the entire image in one go into a neural network. So that is one of the biggest challenges. The challenge is slightly smaller in radiology, where you have images of size 4000 by 4000, but even that is quite big compared to ImageNet, where the image sizes are a few hundred by few hundred pixels. The second challenge, which is the reverse of this challenge, is that the number of images is small. We don't have 1 million, 20 million images in medicine. So if you want to train a neural network for a very specific use case, at most we will have, let's say, 1,000 patients, 2,000 patients, and so forth. So that is not a very large number. And because it's not a very large number, we have to come up with creative ways of using deep learning to train neural networks on small data of images with large sizes. And then the nature of the images is quite different between regular photography versus medical images. So for example, in a glass slide, there is no gravitational orientation. There is no like upside, downside, and horizontal. You can rotate a glass slide and it will still look, you will not be able to tell if I just give you the image and not show you the label of the slide. On the other hand, if you look at radiology, in radiology, there is an up and a down based on the up and down of the human body. But on the other hand, in radiology, what you don't have is scale invariance. So for example, in regular photography, a cat can be close to the camera or far away from the camera. Whereas in chest X-ray, the chest cavity will always almost completely take over the width of the X-ray image. So that is the type of invariances that you will encounter in medical images are different from the ones that you will encounter in regular images. Then there will be a lot of class imbalance. You will not get the same number of images of healthy patients and diseased patients, for example. There will be perhaps more patients without the disease and fewer patients with the disease and so forth. And certain subtypes of disease can be may give you very few examples. So class imbalance is a big problem in working with medical images. Then I already talked about different characteristics also. So there is also other types of differences other than invariances in medical images. So for example, the color space that you will use in pathology is much limited compared to regular photography images, whereas most of the radiology images are only black and white or grayscale. And then you will have uncontrollable data characteristics. What that means is that when you take, let's say, an MRI scan from one scanner and you take MRI scan from another scanner, there will be differences in noise characteristics, contrast, and so forth between the two scanners. What that does is that if you train machine learning or deep learning only on data from one source, it doesn't work very well on data from another source. Unlike a radiologist, any human who's trained on one set of images can easily adapt to a new set of images from a different equipment that looks similar but not exactly the same. That is not the case with machine learning. Because we lose control over what the machine learning model learns, we have to make sure that we train it on a diverse set of data right from the beginning. Then obviously we have concerns about privacy and regulations, that we should have informed consent of the patients before we use their data, and before we use the model, it should have cleared all the regulations and so forth. And this is unlike the image-based applications that you have on your smartphone, such as the one that puts a dog filter or makes a cartoon face out of your face. Those are for fun. So here, because people's lives are at stake, there are regulations in place that have to be cleared before the research can begin and after the research is applicable. But then a lot of these models have become so big in the number of unknown parameters that their decision making has become quite opaque. Even the deep learning researchers, the best researchers, don't actually understand how the model is making its decision. So that is a cause of concern when you use it in medicine, where the mistakes many times you would be asked to explain the mistakes so that we can put corrective actions in place so that the same mistakes don't happen in the future. And then a couple of other things, such as uncalibrated confidence. So this is one of the problems I alluded to earlier, that if you give a neural network an unknown image, it will still confidently predict it wrongly, and its confidence may not be very well calibrated. And then the experiment times are long because you have to validate these models a lot. Any questions before I go further? So when we think about artificial intelligence, there is an entire life cycle of artificial intelligence. We mostly, when we teach courses and we do research in academic institutes, we are mostly concerned with data preparation and then training and validating the model. But there are other factors that we should keep in mind. So for example, we should be making the models for the right cause, which is the economic need. We should be making the models for the right type of data and for predicting the right kind of outcome. And then comes data preparation, that it should be done ethically while preserving privacy of the patient and so forth. Training and validation, it should be validated very well. But then once you deploy it also, and once you package it and deploy it, at that time there should be clear guidance to the user about what the model is meant to do and what it is not meant to do. What kind of patients it was trained and validated on, what kind of patients it was not validated on. So for example, was it trained on children? Is it applicable to children? Was it trained only on men and it is not applicable to women? Was it only trained and validated on a Caucasian population in America, and now it has to be seen whether it really works for the Indian population, and so forth. And then once it has been deployed, it shouldn't be just fire and forget. It should be monitored and audited so that we make sure that the model still works as expected after the deployment. And when we are validating an AI model, we want the model to be validated on tougher and tougher conditions. So at the very least, the patients whose data we use for training should not be used for validation. So sometimes what can happen is you have very large images, you're creating sub images from them, only sub images are being fed to the neural network. Now these sub images, you cannot take the sub images of one patient and put some of them in training and others in testing for the same patient, because the neural network can give you false confidence of good accuracy because it has learned patient specific features as opposed to disease specific features. So the patients should be separated between training and validation. What will be better if we can even separate out hospitals or populations, or even the data acquisition setup, which is the equipment and so forth. That way it will be a tougher test for the neural network, and we'll be more confident that tomorrow if we change the machine that acquires the data, it is still likely to work. So we can use any of the upstream data from the time you collect the data to when you plan the treatment, give the treatment, and you see the outcome of the treatment. You can use anything that is on the left hand side to predict whatever is on the right hand side. So all these are open problems on which we can work. So for example, we can take clinical data, try to predict the diagnosis. We can take clinical and imaging data, try to predict molecular, which is the genomic, what are the mutations in the cancer and so forth. So any of these we can build a model for. So I'll give you some examples of the work that my students and I have done for replicating a human expert. So here, this is a type of a slide that is prepared for breast cancer patients. It's called a HER2 news slide. So here you can see that in this column, you see two patients where you don't see a lot of brown stain. This brown stain is a marker for HER2 protein. And here you see that it has a lot of brown stain. So the ones that don't have a brown stain, they are HER2 negative. The ones that have a lot of brown stain are HER2 positive. Then this one which is weakly positive is also considered negative, whereas this particular one where you see intermediate, which is 2, so 0, 1, 2, 3, this is the ambiguous one. Here we don't know whether the patient is HER2 positive or not. Why it is important? Because if the patient is HER2 positive, then their treatment will change. So earlier, HER2 positive breast cancer was a dangerous form of cancer. Today, it is not that dangerous because we have specific treatments for anti-HER2 therapy. So what you can see is that just the darkness of the image is not enough. What we need to see is whether the brown stain completely encloses a cell or not. It sits on the membrane of the cell or not. So it should form these complete circles, complete like a compartment around the cell. Now that compartment can be light in color, but it has to be complete. Here it is dark, but it is not complete. So this one is actually a lower grade compared to this. So finding this completeness is not an easy problem for other algorithms, but we can train neural networks to solve this. So what we did was we developed a neural network where we fed these images, and we changed the architecture of the neural network a little bit, where we took a side input at one of the intermediate layers. Now, what we did in this side input is we took a control tissue, which is known to be HER2 positive, and we fed its color so that if there is change in color, the change in the extent of brownness from one lab to another, that can be counted. And because of that, we got very good results. And for this particular data set, which we got from University of Warwick, our algorithm performed better than an average pathologist, but not better than, of course, a group of pathologists, expert pathologists, but compared to an average pathologist. So for example, it got 26 out of 27 correct. But that doesn't mean it is ready for deployment, because we got a very clean data from University of Warwick, where the slides were prepared under very controlled conditions and so forth, which will not be the case every time that you get a slide. So now our algorithm can take a slide and it can mark regions that are HER2 positive, regions that are HER2 negative, and so forth. And if we zoom in, we can see that it is marking them correctly. Now, before we take these slides and train neural networks on it, one of the problems that we encounter is sometimes that the color coming from one lab or one scanner is slightly different from color coming from another lab or another scanner. Now, because we don't have control over how these neural networks, what kind of features they extract, sometimes if you just train on data from one lab and you give the neural network data from another lab, it may not perform very well. So what we want to do is we want to take slightly different colored images and make them look like this without changing the structure of the image. So we want, you can see that this is slightly more pinkish and less reddish. So this looks like this target image, although it has a structure of the source image. So that is what we want to do with these images. So one of the algorithms that we developed for this when I was at IIT Guwahati was to do a color normalization. So what we do is we take the pixels of the source and the target image, and we compute its optical density, and then we separate the optical density into two different colors which correspond to the two different dyes. One is the pink dye and the other is the purple dye, so eosin and hematoxylin. So we do that using something called sparse non-negative matrix factorization, and once they are separated, we can take the structure of one image and use the color of the other image, recombine them, and we can get images that are like this. Then further we did a test to show that if we do color normalization, then neural networks perform better because they don't have to worry too much about the color variation. They do not have to learn over the color variation. They can concentrate on only on the shape variation, which is what we wanted. Then the next thing that we did was we developed other nuts and bolts for computation pathology. One of them is segmenting out different nuclei on in cells. So if you look at this image, this circle that you see is one nucleus, the next circle that you see is another nucleus, this is another nucleus, and so forth. This is characteristic of cancer, where you get a lot of cells crowded together, and when you have lots of cells crowded together, then it is difficult to write an algorithm that can separate the boundary of one pixel, one nucleus, from another nucleus. So if you use any of the other algorithms, you can see that it cannot separate out this jumble of nuclei, right? So it cannot separate out nuclei that are touching each other. And then other algorithms don't work very well because, like watershed algorithm doesn't work very well because there's a variation in color here within the same nucleus. Whereas using deep learning, we are able to reasonably separate out all the touching nuclei, all the nuclei with color variations and so forth. So how we did that was we hand annotated lots of nuclei. So these green boundaries that you see are something that we used a digital pen to mark 20,000 nuclei. So once we have marked a lot of these nuclei, then we trained a neural network that can classify whether a pixel is on the boundary of the nucleus, inside the nucleus, or outside the nucleus. And once we can predict that on a new image, and here also we use color normalization, then we can write morphological operations from image processing to separate out these nuclei. So here's a sample again. I will show you in detail that this is one nucleus, this is another nucleus, this is another nucleus, and so forth. And it's very difficult to use anything other than deep learning to separate them out. So here, but our algorithm is able to separate them out very well. Then we took this data and we launched it as a competition in MICAI 2018, where several other teams from around the world used our data to compete with each other to do better than our algorithm. And then they started doing better than our algorithm as well. And then we launched another data set where not only the boundaries of the not only different cells have to be told apart, but also we have to tell the type of the cell. So we launched a data set with 4 types of cells. The advantage of this is that now it gives you a way to study the microenvironment of tumors. So whether there are more lymphocytes present, what is the immune response to the tumor, or more macrophages present or more neutrophils present, and based on that we may be able to predict the whether immunotherapy will succeed or a particular type of chemotherapy will succeed, and so forth. So this we launched as a competition in 2020, and several teams participated in that, and it has come full circle. The first competition that I showed you, predicting HER2, compared to that, so that lab participated in our competition and they did the best in our competition. So first we did best in their competition, and then they did best in our competition. So then we went a step further. This is now we are trying to develop algorithms that can go beyond the human expertise. So before I showed you that, this HER2 positive slide that you see here with this brown stain, it's very easy to diagnose that it is HER2 positive. But if I take this pink and purple slide, which is very less in cost compared to the brown slide, can I tell that this is HER2 positive or not? As you can see that there is a structure, this structure is similar to this structure, and that is because it's the same cancer, same patient's cancer, but two different slices of it. One slice is colored using an inexpensive method, the other slice is colored using an expensive method. So are there subtle changes in the pattern of the cells that I don't need the brown slide to classify HER2 positive patients? This is something that most pathologists will not be able to do. They will not be able to look at this particular slide and say that this is HER2 positive. So we took a lot of these data set where we had HND and HER2, and these were like serial sections of the same patient. And because there were serial sections, we were roughly able to match that this gland is same as this gland, these glands are same as these glands, and so forth. So based on that, if we see that this is weakly HER2 positive, which means it is negative, we can mark these regions as negative. Whereas here we see that it is HER2 positive, so we can mark this as HER2 positive. And this region has no cancer. So these three classes we can easily mark on a few hundred slides. And then we train the neural network on patches from this area, from this area, from this area, to do the classification of the three different types. So whether it is cancer or not, and then within cancer, it is HER2 positive cancer or HER2 negative cancer. So then on the patients on which we did not train, the neural network started to do very well. It can find out all the HER2 negative cancer. This is also HER2 negative cancer. This is not cancer. This is outside the cancer. And this is HER2 positive cancer. And when we look at the serial sections, they match very well. These are HER2 positive cancer. This is HER2 negative cancer. So this is fine. So now we can have an inexpensive test to find different mutations. But what do these mutations really mean? Does a patient really have only one mutation driving the cancer? Which is not the case. It is often suspected that patients who are not easily cured using a particular therapy, that is because they have more than one mutation driving the cancer, and we treat only one of the mutations but not the other mutation. So that is called intra-tumor heterogeneity. So there is heterogeneity within the tumor itself, that it is not driven by just a single driver mutation. It may have acquired multiple mutations. So no one had actually defined how to quantify whether a tumor is homogeneous or heterogeneous before this. So what we did was we looked at something called a genomic signature. For breast cancer, there are 50 genes that are considered important. And if you look at that 50-dimensional space, and within a cohort of patients, you put a point in that 50-dimensional space, you can color those points based on what type of breast cancer they have. Do they have luminal B breast cancer? Do they have HER2 breast cancer, which is the green one? Do they have basal breast cancer or luminal A breast cancer, which is the black one, and so forth? So I cannot show you 50-dimensional space, so we reduced it down to 2-dimensional using a tool called TSNE so that I can display it. And here we can see that there are different clusters, but these clusters merge with each other in some sense. So we defined heterogeneity as whether, based on the ratio of whether the patient is close to its own center or whether it is close to some other subtypes cancer center. So in that distance, we did not just directly do Euclidean distance. We used something called Mahalanobis distance, which gave us better results. And based on that, if we take the breast cancer, luminal A breast cancer, which has the best survival case, there also within luminal A, the cancers that are homogeneous versus heterogeneous, they behave differently. So this is a survival curve. On the x-axis we have time, on y-axis we have survival probability. Initially everyone is alive, at a long time everyone will die, so all the curves will come down. The question is how fast they come down. So we see that using our criteria, the luminal breast cancer that are pure have a higher survival probability compared to luminal breast cancers that are heterogeneous. So this we felt very good about this quantification. People had suspected it, but we had quantified it. And then we looked at other characteristics of these patients, and they were also very different. For example, heterogeneous tumors had larger tumors. They were older women, and they had more mutations that define proliferation of cancer and so forth. So what we want to do with this is, now we don't want to stop at genomic analysis, because genomic analysis is expensive to do for populations such as those in India who cannot afford many of these tests. Maybe in the future there will be a technology to do cheaper genomic tests, but for now we want to work with this inexpensive HND stained slide, and we want to map all the portions that have a particular mutation and all the portions that have a different mutation, so that we can study the heterogeneity, and based on that we can plan cancer treatments better. Then we also worked on taking prostate cancer, and if the patients were treated in one way, but then they diverged in terms of whether the cancer came back or not, then developing predictive models that will tell you whether the cancer will recur or it will not recur. So that helps us be more aggressive on patients where the cancer has a chance of coming back, and being not subjecting the patient to harsh treatments if the chance of cancer coming back is low. So we developed an approach where one neural network found out all the nuclei. So this is where all the nuclei annotation that we did earlier, that came in handy, and the second neural network that classified each nucleus into dangerous or less dangerous nucleus, and based on that you can see that we were able to classify between recurring and non-recurring neural networks better than using some of the other techniques. So now if we want to go beyond just simply annotating regions where we see mutations using expensive tests, how can we modify deep learning to do that? So this is an example of that. Something called weakly supervised learning. So this is a different cancer. This is a thyroid cancer, and here the important mutation is not HER2 mutation but BRAF mutation. So with BRAF mutation, what happens is that if you do a DNA test, you can very easily determine it, but DNA tests are expensive. If you do a IHC test, then the results are not very reliable. Plus, the IHC test is very diffuse, so you cannot mark regions from which you can learn what BRAF positive cells look like, what BRAF negative cells look like. Whereas preparing this slide is inexpensive, but this doesn't tell you about BRAF mutation. So we use a different form of a neural network, which is called weakly supervised learning network, where we not only extract the features of different locations using a neural network, using a pre-trained VGG16, for example, but we have a side branch that tells you whether that location is important or not. So it automatically puts high attention on regions that are differentiative of BRAF positivity versus BRAF negativity. So based on that, we were able to distinguish between BRAF positive and negative patients quite well. And not only that, we were able to actually mark the regions that are important for positivity and the regions that are important for negativity of BRAF mutation. And when we look closely, we see that the cell shapes are different. So pathologists had suspected this earlier, but this was the first time we were able to actually show this using deep learning. And then we are developing other tools for segmenting tissue using multi-resolution units, and we are also using graph neural networks for characterizing the microenvironments of tumor and so forth. Then So what that does is basically it helps us look at the relationship between cells and their neighbors and tell you that if you look at in situ breast cancer versus invasive breast cancer, it will highlight the regions that define in situ, which is the boundary, like this boundary that you see, clear boundary that you see of the tumor. Whereas here, invasive breast cancer has no boundary, it is more chaotic. So you do not get such highlighted results, even using our technique or any other technique. You don't see the highlights. Similarly, in prostate cancer, Gleason 3 versus Gleason 4, Gleason 3 is defined by well-defined boundaries of glands, and we can see that our technique can highlight. So basically, it is going more towards reasoning of how it is making the decision instead of just giving the decision. So that is the next frontier that we want to contribute towards. The next, another couple of lines of research that we are working on, one of them is uncertainty estimation. So what uncertainty estimation means is that, let me give an example. So let's say I trained to classify a condition in colorectal cancer, and based on that, I can tell whether it is no cancer versus colorectal cancer. But what if I give very uninformative images, such as a bunch of red blood cells or a bunch of the fat tissue or no tissue at all? In that case, the neural network should be able to say that this is uninformative instead of forcing the decision that it is cancer or no cancer, because it doesn't know. It hasn't seen enough of informative regions of the tissue. So for that, we have developed a method which is based on supervised SIM-CLR network, which can distinguish between informative and uninformative, or out of distribution versus in distribution images. The next thing that we are working on is training neural networks that are tolerant to mislabeling in the training data itself. We usually take training data as we assume that it is correctly labeled, we assume that it is the ground truth, it is the gold standard, but that may not be the case. The training data labels have to be provided by doctors, and there are sometimes disagreements between doctors, or sometimes they loosely mark a region where they go outside the boundary of what they are supposed to mark, or they are inside the boundary of what they are supposed to mark, because they don't have a whole lot of time. In that case, we would like to be able to discard those sub images that are wrongly labeled. But how do we know it is wrongly labeled if it has already been labeled by an expert? So here what we do is we train the neural network assuming that it is correctly marked for a few iterations, and then we get a distribution of the loss function on the images. Those at the tail end of the loss function, we assume that these images are wrongly marked. So we identify the tail, and then we discard this portion, and we then only train on the cleanly labeled one, and we get better results. So we show that using this method we can improve the results, and we can also show that the patches or sub images where the loss is high, there we can see that these are uninformative patches, whereas where the loss is low, that means these are informative patches, they are correctly labeled. Okay, so that's it. I can take questions now.
Yeah, thank you, Sethi. And now I request the audience, students, to ask questions, the doubt.
So may I ask a question?
Yes.
Yes. Sir, in case of HER2, sir, you have used, I think, CNN, I think Google Net, and in thyroid cancer, you have used VGG16. So I want to know why and what points should we consider while using implementing architecture.
Right. So for HER2, what we used was actually that work was done before Google Net. So, and then at that time we did not have a very big GPU with a big RAM. So that was actually not a very deep network. It was not as deep as Google Net. It had only 8 layers, if I'm not mistaken. But later on, we had GPUs with larger RAMs, 12 GB RAMs, for example, then we were able to use VGG16. But this was a pre-trained VGG16, so we did not actually have to use a very large RAM. So a lot of it depends on one, the type of problem you are solving, and two, the type of resources that you have. Some networks will not fit on your GPU RAM, for example. You cannot always use DenseNet 150 layer DenseNet on the kind of GPUs that you have available. And the other thing is that these patterns of pathology are slightly simpler than, let's say, finding out what object class out of 1,000 different object classes are there. So because of that, you can use simpler networks sometimes for pathology and radiology, depending on which architecture you use.
Thank you, sir.
Yeah, but there's no set formula. It comes only, with experiment by playing with a few networks and a few types of images.
Okay, sir.
Any other question? Because this is very interesting. A lot of questions should be there. I have one or two questions.
I see a question from Hilal.
Yeah.
Let me read it. Sir, if label data is not sufficient, shall we go for unsupervised methods for segmentation? So instead of unsupervised, what I will say is that pre-train the network using self-supervised methods, and then fine-tune it using few shot learning. That might work better. You can also use some unsupervised methods such as GANs or VAs. Yeah, go ahead. Yes, please.
Yeah, like the problem is like because we have how you actually whether the data are available in the public domain, or like we have to how to get this type of data. Like you have shown some histopathological data, so
yes,
are they available in public domain, or like for like beginner, like doing who wants to start up do some research here, they want to start in this field,
right.
So how they can proceed actually, whether this
right. So there's a lot of data available in public domain. For example, the TCGA, or if you go to GDC portal, that has a lot of data that is already available. Good evening, Professor Bora. How are you? You are muted.
Yeah, I'm fine.
Good to see you after so long.
If you allow, we have a couple of questions from our this online YouTube, from the YouTube. This Kyoyo Robert, he has a question. Is there a possibility for the neural network to be trained to give quick prescription as soon as the patient is sick?
That's a dangerous proposition, because and I don't think that is possible today, because a good doctor should try to get to the root of the problem, and that is a very interactive process. You ask something, you test something, and when the result comes out this way or that way, then you do another test and so forth. So that's a very unstructured problem. Neural networks are only good with very structured problems.
Another question, I think he's answered, and another question from same this sputum smear images for training.
Can you please repeat?
Can I use sputum smear images for training?
Sputum smear, yes. So you can, but then you can use that, for example, for diagnosing TB and so forth, using Leishman-Ginza stain and so forth. So, but that has to be first, the ground truth has to be established using either through the feedback of the doctor or through another test. I think there is another test that is more authentic, or more of a gold standard for determining TB. But yes, that's a good problem that you can work on.
So another question, but it is same as what we have discussed already. So are there some online repositories where one can get images for training? So
Yes.
this another question. This I think already answered.
Yeah,
And,
go to grandchallenges.org, Kegel Grand Challenges. So I will write it. Grandchallenge.org, Kegel.com. These are good ones. And then GDC site. Just look for GDC, you will find it. And then Cancer Imaging Archive. So these are sites where you can find tons of
very
data sets.
it will be quite helpful and informative. Okay, I hope. So I have one question. Like you have proposed this for the histopathological images. So I think how you actually do, in accuracy, suppose in terms of accuracy, how
Yeah.
you compare it with radiological images, like for screening. So for suppose early detection for screening purpose. So
Right.
can you go for radiological images or whether they are comparable with this pathological images, histopathology?
So radiology images are they are what is called non-invasive. You don't have to get inside the body to create the image. So that is their appeal. But the more authentic analysis can only be done by looking at pathology, which is you are looking at the cell level and the tissue level. So for screening, definitely radiology is the way to go. But then for the final diagnosis, pathology is the way to go. Pathology or molecular test.
So thank you, Professor.
Okay,
Yeah,
excuse me. I have one question,
please.
Professor Sethi. In case, suppose if the data set doesn't have sufficient labeled data, the labeled images. So in those cases, I've found some literature where they said, I think if I'm not wrong, some Nature papers. So they said that if the labeled data are less, so in those cases, the handcrafted features or the handcrafted based techniques are much you can say they dominate over the deep learning based networks. So
Yes.
is it true?
Depends on the problem. In some problems, it using than a simple classifier like a support vector machine or even logistic regression might work better, or random forest that might work better.
Right.
But now the data is it's expanding quite rapidly, number one. And number two, we have ways of pre-training neural network on other data and then still make them useful on a smaller data. So because of that, even the features for SVM or random forest are being extracted using lower layers of a neural network.
So the pre-trained networks, not necessarily with that class of images, so
Yes.
can be well used with the
Yes.
okay.
Yes, like we use VGG16 for thyroid cancer, that was pre-trained on ImageNet.
Right. Okay. Thanks. Thank you a lot.
Okay.
So in we have also seen some medical imaging problem, like people use the pre-trained networks. So when data is there is less data, so data is not available. I think the pre-trained networks are also possible to be used. I think.
Yes.
So yeah. So thank you, Professor, for your nice, very informative talk. I think we have come to know a lot of new things from your talk. So we have with us now our next speaker, Ratul. Can we proceed?
Yeah, please go ahead.
Yeah.
I'll sign off. I have a class to teach.
Yeah. Thank you so much, Professor Sethi. So yeah, thank you.
Okay.
Thank you.
Bye.
So we have with us Professor P.K. Bora, sir. Good evening, sir.
Good evening.
So, sir, a little introduction before starting the talk. Professor P.K. Bora is professor at the Department of Electrical and Electronics Engineering, Indian Institute of Technology, Guwahati. He has obtained his PhD from Indian Institute of Science, Bangalore, and joined IIT Guwahati in 1997. His research areas include image processing and computer vision. He has published his works in journals of repute like IEEE Transactional on Information Forensics and Security, IEEE Signal Processing Letters, IEEE Communications Letters, IEEE Sensor Journal, Pattern Recognition, and Biomedical Signal Processing and Control. So I request Professor Bora sir to start his talk.
Okay, thank you for the nice introduction. So I'll just see. Is my screen visible?
Yes, sir, it is visible.
Yeah, but yeah, I'll just.
You can share yours now.
Yeah. I'm scared. Yeah. So title of my talk is Application of Deep Learning in Communication Engineering. It is slightly different. This slide is visible, no?
Is it visible, sir?
Okay.
I think our other participants also can see this slide. Is it visible, participants?
Yes, sir.
Yes, sir.
Colleagues? Okay. Yeah.
So I'll give introduction to machine learning and deep learning, then deep learning applications. Just 1 minute. Deep learning applications to wireless communication, classical approaches to blind modulation classification, and DL-based blind modulation classification. As you know, machine learning enables computers to act without being explicitly programmed. It is totally based on data. ML algorithms are designed in such a way that they can learn and improve over time when exposed to new data. So basically, we have the training data. From training data, feature is extracted. Machine learning algorithm will classify group of objects, or it can predict. So a traditional machine learning versus deep learning. So in machine learning, feature extractors that you have to devise, they are handcrafted features. It means that you have to apply some algorithm to extract the features. And these features are trained with a trainable classifier. And in the case of, so that is the traditional and modern, even mid-level, features are extracted using some unsupervised methods like bag of words. Now, in deep learning, all these levels, low-level features are learned, mid-level features are learned, high-level features are learned, and there is a trainable classifier, all are clubbed together. Okay. If we go back to machine learning, the whole perceptron model is the basic example. It is a mathematical function to model the biological neuron, but it is approximate model only. The mathematical function involves nonlinear mapping of the weighted sum of the inputs. So you see here, so these are the input x1 to xn, and each input is weighted, and then some bias is added and then added. Then after that, we pass it through some nonlinear function. And so that will give you the classification or whatever purpose it is. The mathematical function involves nonlinear mapping of the weighted sum of the inputs. The perceptron weights are learned, and the model is used as a linear classifier for binary classification. But perceptron is a linear classifier only, so how to apply it for nonlinear classification? So for that, artificial neural network, ANN, it is a collection of connected units of perceptrons called neurons. Okay. It is also called multilayer perceptron as it usually has multiple layers of neurons. Like first layer is called input layer. Then suppose from each neuron in the previous layer, there is connection to all other neurons in the next layer. So it is also called multilayer perceptron as it usually has multiple layers of neurons. And ANN with many layers can learn a nonlinear decision boundary. That is the initial problem of perceptron was that it could not find a nonlinear boundary. But that problem is solved with the addition of the hidden layers. And ANN is trained using gradient descent algorithm. That algorithm I will tell. So I will consider one simple example, linear regression. So learn a mapping function, y prediction is equal to fx. Some data is there. On the basis of that, some argument, suppose x, on the basis of x, what should be the prediction? So the simplest function is the linear regression model. Y pred is equal to ax plus b. This can be done using a single neuron, ax plus b. Okay. This mapping function can be used to approximate the new value of x. Approximate for new value of x. Suppose at some other point here, what will be the predicted value? Because of we know this line, we can predict it. Okay. Now training the regression model. Training the regression model involves finding the best fit for the data. Okay. So this is achieved by minimizing the error between the y predicted and the actual value, y actual. A loss function or a cost function is to be minimized. That means in suppose a neural network, always it is an optimizer. It optimizes a cost function, and simplest cost function is the mean square error. The mean square error is defined like this. This is the observed data, or this is the actual data, and this is the predicted value. So error square, and then you sum up divided by n. Now how we will solve this problem? So the partial derivative, we have to solve it because it is a two-dimensional problem. We will take the partial derivative with respect to a and partial derivatives are 0. So that way we will get one equation here, and with respect to b also we will do the same partial derivative, and equate to 0 we will get another equation. So solving 1 and 2 we get a and b. So this is the exact method for solving the problem. Now what is gradient descent? So gradient descent, so we know these are the derivatives. The values of the parameters are updated using a rule, what is based on the gradient. How it is done? That is, new value of a will be old value of a minus mu times the partial derivative. Okay. Similarly, b new is given by this, and these two I can represent in terms of a equation like this. Suppose single equation if I write, that is AB vector is equal to okay, yeah. So AB vector is that is A1 old, B old, and then minus mu times the gradient of MSE. Okay, so this is the gradient based on the gradient. Where gradient, what is gradient? Gradient in this case delta MSE del A and delta MSE del B. It is the vector composed of that. Now, this rule, if we start with any point, suppose initial point, and then it will move along the direction of the negative of the gradient, so that we can get the minimum here. Okay, this is the gradient rule. But in deep learning, we do not use the exactly this steepest descent or gradient method. Training using the stochastic descent or stochastic gradient. What is that? It is an iterative method. So what is the principle? New weight vector is equal to old weight vector minus step length into gradient vector. That is the basic. Since the gradient is a function of the direction of maximum increase, the negative of the gradient is the direction of maximum decrease. Here we are minimizing the cost function. That's why we have to go to the direction of maximum decrease actually. All the data points are used in computing the gradient. You see here, to determine the partial derivative, we are using all the data points. Yi, I going from 1 to n. Okay, so now that is the problem. And when we consider this, suppose in a very large network with so many parameters, then we have to use so many data and for so many parameters. So it is really computationally exhaustive. Since the gradient of a function, okay. So what is the solution here? We apply this stochastic gradient descent algorithm. What is stochastic here? A few samples are selected randomly instead of the whole data for each iteration. For each iteration, we do not consider all the data, but part of the data, but that we have to consider randomly. Weights are updated intelligently. Weights are updated intelligently using the backpropagation algorithm. Okay, this is also another interesting thing, backpropagation. Backpropagation algorithm. Okay, so what is backpropagation? Because you have to train all the layers of the network, but all the layers do not involve the output variable. So how to propagate the error from the output layer to the inner layer, that is also interesting, and that is interestingly done in the backpropagation algorithm. So therefore we have to, what we have learned, that we have a network. Now training means we have to learn the weights and biases in the network, and that is done using by minimizing some cost function, which is a function based on the error between the predicted value and the true value of the training data. And the algorithm is deepest descent algorithm, but since we have only we have huge amount of data and huge amount of parameters, so we cannot directly apply the deepest descent algorithm. Only few data points are used randomly in each iteration. That way we get this stochastic gradient descent algorithm, and under certain assumption, this algorithm converges to the true minimum. Okay, and we have learned that there is the backpropagation algorithm, which then there is something called pooling. Then there will be again convolution layer. That way there will be multiple layers of convolution. Then finally this convolution and pooling layers will continue. I will explain those. And then finally whatever we get after the final convolution and pooling layers, that is flattened. This is converted into a one-dimensional vector, and then we apply a conventional neural network of one or more layers. That way, this is the basic structure. So that way, we have convolution layer, pooling layer, and fully connected layer. We'll explain this. Convolution operation, we know this is the convolution operation. Suppose XN and HN are two samples sequences, then we know that convolution is given by this basic operation. Summation xk into h sub n minus k, k going from minus infinity to infinity. Okay. And this can be written in the other order also because of the commutativity of the operation. In terms of linear system terminology, SKs are called filter coefficient, and normally we will consider only finite number of filter coefficient, so that way the convolution can be written like this. So this is the basic convolution operation. Why it is important in our purpose? Because it is a local operation. Unlike in the case of neural network, where a neuron is connected to all the neurons in the next layer, unlike that, in the case of convolution only, it is a local feature extractor through a local operation of sum and that is multiplication and sum. That is the basic operation involved. That is also a very simple operation, and it can extract features from data. So this convolution layer is the core of the CNN that performs feature extraction using convolution operation. The layer is parameterized by learnable kernels. Unlike in the case of suppose normal filter, kernels are known, but here this will be it is to be extracted from the training data itself. The convolution with multiple learnable filters result in feature maps that represent different characteristics of the input tensors. Conventionally, multiple such convolution layers are cascaded in CNN to extract discriminative hierarchical features. So, if we consider the suppose input volume I, because it may be suppose RGB image, so that way we can write the for a 3-dimension convolution can be written like this. Okay. Then activation layer. The activation function are nonlinear transformation applied to the output of the linear operation like the convolution. Without the nonlinear activation, the neural network would perform only linear function. So that way, layers or single layer ability and the creation of complex function during the learning process. Okay. So what are the nonlinearities generally applied? This is the sigmoid, that is sigma x is equal to 1 by 1 plus e to the power minus x. Similarly, then x up to 0, whatever input is there, the output will be equal to 0, and then according to line. So sigma x will be equal to x after x equal to 0. But it has certain problem because of this flat line. So because of that, leaky ReLU is used, which is given by sigma x is equal to maximum of ax and x, where ax is the slope of this line, which is usually a small quantity. Okay, so we knew what is the activation unit, what is the convolution operation, then we'll get the pooling layer. This layer fuses the neighborhood spatial information from the feature maps using average or max operation. Pooling reduces the spatial resolution of the feature maps thereby reducing the number of parameters and improving translation invariance. This is an example of pooling. So from these 4 blocks, we are getting only 4 elements. Each block taking the maximum value of the block. For example, here it is for this block 23 is the maximum. Okay. Now, what is the fully connected layer? That is the actually neural network. The output feature maps of the final convolution or pooling layers are transformed into a one-dimensional vector and connected to one or more fully connected layers. These layers are dense layers where each node is connected to all the nodes in the previous layer by learnable weights. The final FC layer, also known as the output layer, contains the same number of neurons as the number of output categories with a softmax activation function to obtain the class probability. Okay, so that way, if we have a image, suppose convolution, so this is intermediate features, then flattening, then fully connected neural network. Here it is a 3-layer network, and then since here it is a binary classification, so output is only 1 layer. So that way we know the basic structure of the CNN, and what is this difference with conventional neural network. That suppose same purpose, if we want to perform with a neural network, suppose, then we will require so many layers of neural networks, and it's performing global operation, which is computationally very exhaustive. So that way, CNN, because operations are local, and how to reduce the features, dimensionality, how to reduce. There are different ways are there, like pooling, dropping, etc. And that way we can get a simpler architecture compared to the deep neural network. So these are some of the architectures like InceptionNet, ResNet, etc., which are very popular. And other deep learning network approaches like long short-term memory or recurrent neural network. They are used for predicting future values in time series data. Autoencoder used for learning inherent low-dimensional structures present in data. Encoder-decoder network used for pixel-wise classification of images or videos for simple segmentation tasks. This is one important architecture. Generative adversarial network can learn the probability distribution of the input data, and hence can generate a realistic looking artificial data. That is the importance of GAN. So it is based on the adversarial principle, and it can learn the actual probability distribution of this data. And if we know the probability distribution, we can generate a realistic looking artificial data. And there is a lot of application field, but classically they are used for image classification. Brain neural networks perform better than human on famous image datasets like deferred, etc. Text generation, the networks can model the next element in a sequence of elements if trained with appropriate data. Generate handwriting. Okay. Language translation, it is very famous, like Google Translate. Recently, DL has been applied to different areas of communication. That is our focus. Okay. Okay, then I will go. So a traditional communication system, what is there? There are blocks like source encoder. So here symbols will be, suppose source symbols will be there. It will compress actually. Then channel encoder, it will convert it into a chain so that error can be detected. Then modulation pass to channel is the receive signal. Actually, this is the receive modulated signal. So these are the blocks of communication system. Source encoder. Suppose we have some message, and that message will have some symbols. Those symbols are to be coded properly so that we can have a compressed stream of data. Channel encoder. Here redundancy is added to the bit stream so that error can be detected. Then it is that signal, that symbols are modulated with the help of some carrier. It is modulated, and that modulated signal is passed over the channel. And in the receiver side, we get the received modulation signal, which is passed through a detection. Here we have to know the channel information, and from the channel information we can extract the modulated signal. Actually, that is detection, and we have to do demodulation, then channel decoder, source decoder. Ultimately, we get the received symbol. So, in a nutshell, these are the activities of the traditional communication system. Now, how machine learning, deep learning can be applied? Machine learning and deep learning application, like it can be applied channel encoding and decoding, channel estimation. It can be applied to channel estimation and signal detection, resource allocation, automatic modulation classification, that I elaborate, and end-to-end communication system. This entire system can be represented using a network. The entire symbol, from the symbols to the source decoder, everything can be put into a single network. Okay, example, ML-based end-to-end communication system. So there has been application of what is known as the autoencoder. So this is an encoder network. It is a stack of convolution layers, and the input data is converted into a latent representation, which has lower number of bits. Okay, this is the original. Suppose it is a very large number of bits, so encoder will convert it into a latent representation. Now, this channel, it will be during training, for example, this channel we can take. It may be usually the proposed paper they have used AWGN channel, and then this noisy data, from the noisy data, then decoder will try to reproduce this. During training, it will try to reproduce this. Since we know X, we know we will have some X test. Now through learning, through stochastic descent algorithm, we can train it both encoder and decoder network till we get the reconstructed output to a reasonable accuracy. So this network has shown to perform better than the conventional communication system. Okay, so that we see that an encoder-decoder network can be used as a communication system. And okay, so during suppose a practical deployment, this encoder and decoder will be separated. Now we will go to what is known as automatic modulation classification, AMC. Automatic modulation classification, the objective of AMC techniques is to discriminate the modulation types of an unknown communication signal at the receiving end. So there is substituted signal and it passes through channel receiver, and in receiver we do not know the modulation type. So AMC technique will be able to find out the modulation type. So this is the nice introduction to this topic. Now here signal model, because that received signal is our model. This signal can be represented with the effect of channel and the noise. That complex signal is represented like this, where XL is the modulated signal, this is the modulated signal, and A is the scaling vector, S is the channel response, T is the symbol period, T naught is the timing error, F naught is the frequency offset, and Bn is the additive complex Gaussian noise. So that way we have a communicated signal, or this is the modulated signal. AMC problem is to identify the modulation employed in X from the received signal Y. So this Y we are receiving, we have to find it modulation type of X. AMC started with the likelihood-based approach. Basically what it is done is, like suppose all modulation types, each modulation type is posed as a hypothesis, and on the basis of the received data we have to find out which hypothesis is true. Later, Fisher extraction and classification gain importance. This is known as Fisher-based AMC, and recently deep learning has been applied for AMC. Consider it as a pattern classification problem. Like Fisher-based also considers AMC as, because it is a classification, and from the data we have to extract some pattern. That is the basic idea. So basic network structure is like this. So we have to train a deep learning network. Now how data will be fed? Either constellation diagrams can be data, IQ can be data, amplitude and phase can be data. Because somehow we have, because we are mimicking the image-based CNN, therefore we convert the communication signal into an image. So constellation diagram is a two-dimensional diagram that can be image. IQ data, because in phase and quadrature phase of each signal at this point will be there. That way it is a data, it is an image, 2 by n dimensional image. Similarly, amplitude and phase, that we can represent in 2 rows, so that way this will also give image. And then train the DL network. Now once we have it for the unknown signal, convert it into DL input, pass it through train DL network, and this will detect the modulation type of the modulation scheme of the signal. Okay, this is the basic principle. Research are experimented on different data representations. A complex baseband signal represented as in phase and quadrature components gave data results for CNN classifiers. If you have n complex baseband symbols, it can be represented as a real two-dimensional vector of size 2 by n, where one row represents in-phase components and the other represents the quadrilateral force phase components. Also, Mendelian phase representation of 2D was used. Okay. For example, it is a complex signal. It is 1 by n actually, but in phase component one row, what is a phase component another row. That way it is converted into an image. Now, how to get the data set? Generate the data set, because we have the model of data. First, we get public data set, select CNN architecture, train and validate using data set, test the classifier using test data set. Over here, measurements of 24 digital and analog modulation schemes spreading in a wide SNR values. Similarly, this is another data set. I'll give one example. So, example of CNN-based AMC is full of modulation considered. In this problem, I have PPSK, QPSK, 8PSK, 16QM, 64QM, etc. For this example, this data set is generated using MATLAB. Now, this is the network, this is the input. So that way we get the detected modulation class. The network is trained on the dataset using appropriate GPU. Different platforms frameworks are used to implement deep learning projects such as MATLAB, Python, etc. Most of the researchers employ Python-based frameworks such as TensorFlow or PyTorch. So results of AMC can be reported either using the percentage of correct classification or by comparison metrics at various SNRs. It is shown that these results outperform the traditional works like LB and likelihood-based and feature-based approaches are there. Compared to that, this learning-based AMC gives better results. Current status of the ElDeS AMC works. Many modifications of the CNN structures are being proposed by the researchers to improve accuracy and to optimize the size of the network. That is the one aspect. Another aspect is the ElDeS AMC of MIMO signals, multiple output, especially the internal signals, are gaining popularity recently. Okay, so that way deep learning has been applied for modulation classification. We have an unknown communication signal. We have a communication signal. For example, you want to suppose interrupt enemy's transmission. You want to interrupt enemy's transmission. Then you can find out the modulation class of the enemy signal by using blind modulation classification technique. And DL approach has proved to be more successful than the conventional likelihood-based or feature-based approach. To summarize, in this lecture we introduced machine learning and ANNs, explained the stochastic gradient descent algorithm, learned CNN and components, and introduce DL application to a communication system, and discuss AMC using deep learning. Okay, so that's all. So you have any questions?
Yeah, thank you, sir.
Yeah.
So it's really very nice to hear from you. It's very introductory and also very informative. Towards the end, actually, real applications we can see for deep learning, how we can apply this for unknown signal detection in communication. So I now request the participants to take Bora, sir. I have received one question from his Nuraj Gupta. Question is, can you explain practically how we can create neural network?
How you can create neural network? Practically.
Can you explain practically how we can create neural network? He is a student maybe, so he's Niraj Gupta.
Yeah. So neural network, because it is implemented using, suppose normally it is implemented using a computing platform. So that is also practical. But maybe some VLSI system improves later on, maybe that neural network may be implemented practically. But right now, it is based on computing platforms only.
I think your question answered, Niraj. Okay, Niraj is setting from YouTube where he's asking. Okay, so any other question from the participants? Yeah, so you can write your questions also in the chat box. You can take some questions. So, sir, I actually I have just a query. Actually, in this deep learning scenario, can we, sir, actually for real-time application, like you require a lot of hardware for like GPU. You want to for training. So how do you can reduce the computational time, and how we can make it real in real-time application, like for mobile application? So how we can apply this type of approach, deep learning approach?
Because training is anyway offline. So training is not a problem, but critical deployment will be always online. So for that, the network parameters should be as less as possible. That's why now suppose there are different networks developed, like Inception net, which involve less parameters. Okay, so that way, depending on the problem, suppose you have to optimize the number of layers and appropriate pooling you have to use, appropriate bulk you have to use, somehow you have to reduce the number of possible parameters. Only in practical deployment that time will be less.
Okay, sir. So there is some actually noise in the network. I think network issue is there. Today is thundering actually. So here, so maybe it's actually I could not properly hear your voice. So I think Ratul, yeah.
Yeah, so if there are no questions, then very informative talk, and thank you so much, sir.
Okay, thank you.
Sir. Okay. And I think I also request the participants on behalf of the organizer, like you have to send your feedback. So feedback form should be sent to you. So you fill the form and send back to us.
And also, if meanwhile you have any questions, then you can write to us. Then we will send it to Professor Bora sir for any query. Okay. So with this, thank you all the participants once again. Thank you Bora sir, and thank you Deka sir. Thank you all.
Feedback from the chat box.
Thank you, Ratul.
Yeah. So feedback form is being sent in the chat box. So please fill up the feedback forms. Thank you so much.
Okay. Bye.